So, welcome back friends for another lecture on quantum field theory and quantum entanglement, and we have been looking at the interaction picture, okay, in the last class what we have, okay. So, the interaction picture, the basic idea here is that, okay, we have done the quantization of free fields. Now, if I add interactions into the theory, like for example simple interactions, we can think of our electromagnetic interactions or self interactions for a scalar field theory. That is the example we started off with in the previous lecture. Or then you can also have, of course you can also have quantum electromagnetic interactions. You can also have Yukawa interactions in which two fermions come together and they couple with a scalar essentially, which is like a Yukawa interaction in the non-relativistic limit, which gives you the nuclear force essentially of the Yukawa, okay. So, there are this all there are fundamental forces in nature. There are these four fundamental forces. You can think of for the present we will leave out gravity out of it, but other three forces you can think about: electromagnetic forces, strong and weak interactions and everything. This picture can really come up in a quantum field theory. You can think of these three interactions in a quantum field theory. So, the example we started off are the self interactions, essentially interacting scalar field theory. Okay, so this the Lagrangian, the interaction part of the Lagrangian is I just ordinarily put it already, lambda 4 factorial phi 4 essentially, which we call as the phi 4 theory. So, then along the way we derived the Dyson formula for this theory. And the Dyson formula, what does it do? It only just makes the time ordering of the integral which we are trying to solve essentially, because in the interaction picture what we said was that the operators, the states evolve purely with respect to H interaction, and whereas the operators evolve with H0 essentially, because we start defining the total Hamiltonian in terms of H0 plus H interaction, and the states in the interaction picture evolve with respect to H interaction, and the operators evolve with H0. So, this was the basic so it is a mixture of both the Schrodinger picture as well as the Heisenberg picture. So, this makes thing essentially, this makes the interaction picture into some sort of a third picture compared to the Schrodinger picture and the Heisenberg. So, it incorporates both the ideas of both of them. So, this is what we have been looking at, and then in the interaction picture we solved for this equation, which we wrote it down in particularly for this one. So, I del by del t psi I is equal to H I psi I. Now, so while so this we had to solve it carefully, because H I is in the interaction, Hamiltonian interaction in the interaction picture. So, H I is actually again e power I H0 t H interaction e power I H0 t. Okay. So, okay, and then we try to solve it with a U matrix essentially, and then we found out there is a time ordering part of this U matrix. So, let me just revise you the U matrix definition. So, you use a unitary time evolution operator essentially t to t0 unitary now the basic idea is that psi I of t is given by u at t0. So, if you start the psi I at t, just trying to remember the notation which I did last time. I think this is what I used. I think t is the final time and psi t0 is the initial time. So, u will take it from t to t0 u psi I so if you start the interaction picture state at t0, u is a unitary time evolution operator which takes it to at a time t essentially. So this, and then what we have, just a revision of last time, du by dt is equal to hi of u, and this is precisely what we were trying to solve essentially. So we wanted an expression for u as it evolves in time, so that I can plug back this expression into this, and then I get this evolution of the state essentially. So, and here with this we encountered the Dyson series, which we showed finally that this is equal to 1 minus I integral t0 to t dt prime hi of t prime, okay, plus minus psi square t0 to t dt prime, again t0 to t prime hi of t prime hi of t double prime plus so on. So this series we derived it in the last lecture. Now we had an issue with the double insertion of the Hamiltonian, interaction Hamiltonian, and then we carefully redid the units, and so the limits, and such that we can write an expression in this particular fashion, and this expression turns out to be time ordered essentially. So time ordered means that operators which are time ordered, I think it's okay to revise this thing which I have mentioned it several times, but anyway in the last class. So time ordering is essentially, because this will be useful for today also. So T1, if you have two operators at 2 times O1 and O2 at 2 times T1 and T2, the time ordered product is O of T1 O of T2 when T2 greater than T1, T1 greater than T2, and the other one is O2 T2 and then when this is T2 greater than T1, okay, yeah, that's right. This makes sense essentially that yeah, when T1 is greater than T2, then you have this O1 O2, this is the time ordering you have, okay, and so you always have the earlier time coming before essentially, that's the point essentially, okay, and then yeah, okay, so this is the time ordering, and this is the Dyson series. So now we can now move towards examples of scattering essentially. So what we have set up so far is already good enough to understand how the interaction picture, in the interaction picture you can actually try to calculate a scattering process essentially. So that's a basic most important thing in quantum field theory. So we'll set up this so basic thing of scattering. Okay, so before doing scattering, let's just have some basic idea. So let's so everything, let's try to visualize what we are trying to achieve in this scattering, what we are trying to do in this particular thing essentially. So let's consider example. H interaction is equal to L interaction. Okay, so let's take one simple example. Okay, the example we considered essentially is phi 4. Okay, so there are 5 fields, so it is phi, 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 phi. Okay, okay, so there are 5 fields, each at the same space time point. So that's how you define your interaction. Okay, so phi at x, phi at x, phi at x. Now what it tells is that when a state starts, essentially it evolves only with in a time order products method. Essentially that's a basic idea to take care of causality and everything. So what we are looking at this and we will see later on that time order product should be equivalent to a normal order product plus all contractions, which is called the Wick's theorem. Okay, so but just have a first look at what this means, essentially what this means. So each phi, if phi is real, okay, and then we'll make it complex and then we'll see what happens. Phi is real, so it has an A and an A dagger. Okay, okay, so it has a positive wave functions as well as a negative wave function, so it creates positive energy wave function. So if it creates positive energy, what does it mean? That at you have a product of 4 of this phi 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 here. You can think of the fields you are creating these pi fields. So the real scalar fields, like examples in real life are some Pion field, one of the first elementary particles. Okay, other than the muon, electron, proton, neutron, Pion, say for example, Pion is a real scalar field essentially. So you are creating at the same point, if you have 4 A daggers acting on vacuum, you are creating 4 pi particles, essentially pi particles. So you are creating at this is the interaction vertex, so you are creating 4 pions at that particular state. You can also have pi and 2 annihilating, essentially. You can, all this are possible in this particular vertex essentially. So 2 of them can be annihilating and so on, so essentially. Now it is better, let me take you another example. So if it is a real scalar field, say instead of a real complex scalar field, this is has charged. So pions, neutral pions don't have any charge. So complex scalar field, things are different. You have pi star, pi star, pi. Okay, because the total Lagrangian is real, so you should have pi star pi and pi star pi. In this case, you have one A dagger, one A dagger, another A. So you have 2 particles which are being created and 2 particles which are being annihilated of the same type of charge, okay, or the other way around, okay, because you have the other particle being created. Also you can also have other particle essentially B, okay. So B, so because it's a complex scalars field, we have 2 annihilation and creation operators, one is A and another is B essentially. So you can have A dagger and a B and A dagger. So one kind of particle is being created, another kind of particle is being destroyed. So you can put opposite charges on the vertex essentially. So one charge is incoming, other charge is outgoing. So outgoing from the vertex, 2 charges are outgoing from the vertex and 2 charges are incoming to the vertex essentially. So this is what you mean by this particular interaction. So what you are trying to do is at an interaction at the same space-time point, you are annihilating some particles and creating other particles essentially. Okay. Another interesting example would be the Yukawa interaction. So, let us take H interaction. I have not introduced fermions yet, so but let me just say there is an interaction. So, psi is a Dirac field, same degrees of freedom. We will do the Dirac field in the next lecture or so, essentially as a complex scalar field. Okay. Psi is a Dirac field which we will start doing essentially. So, here also what we will see is essentially that now psi has okay. So, like I said, phi is A plus A dagger. If it is a real scalar field, let us just say real scalar field. So, Dirac field has the same degrees freedom as a complex scalar field. So, psi would be some B plus C dagger, and psi dagger would be B dagger plus C. B dagger plus C. So, similar to like what we have done here essentially. So, you can have A to be A plus B, B star, this would be something like B dagger plus A, okay, this would be A dagger plus B. So, this would be B dagger plus A, okay. So, this would be this. So, similar to this what we have written, okay, maybe I will write it down neatly. Specifically, so this would be, so that the notation is same for everything. So, B dagger, so this is A dagger plus B, this would be A plus B dagger, A dagger plus B. Okay, so psi would be something like this, B dagger plus C. So, this Yukawa interaction is like a nucleon interaction with pions, essentially nuclear force essentially. So, this is nuclear force, nucleon pion interaction. So, pions are this real scalar fields, and nucleons are this proton or neutron which are fermions, spin half particles. So, at a given state, okay, at a given, if they are all at the same point essentially, like for example what I am writing. So, what does it do? If you take an annihilation operator, say for example, it can, so this interaction, say for example, can annihilate a meson in principle. A will be acting on the vacuum and it annihilates a meson, or on the meson state, you start with a meson state and then it not on the, okay, it annihilates the meson and then creates at the simultaneously it creates nucleons. Okay, these are nucleons. Okay, these nucleons are created. The exact interaction actually has much more complications. It also has the SU2 theory, SU2 symmetry, isospin symmetry, and so it will be has more. This is the standard Yukawa interactions, 2 fermion and a scalar. So, what does this interaction do? It annihilates a meson, creates a nucleon antinucleon pair, or you can always say that it annihilates one of the nucleons, creates the other nucleon and a meson, creates the other nucleon and a meson. So, this will be responsible for say some nucleon decays, like okay, some of this decays, or for the nucleon pion neutron protons scattering and so on, so in the state. So, these entire things can be understood in terms of something called this entire process, the process of scattering in quantum field theory is understood in terms of an S matrix. Okay, in terms of an S matrix. So, here what we do is we assume incoming states and outgoing states are free particles. So, the initial states and outgoing states are free particles, but what happens is in the limit t tends to say plus minus goes to infinity, say for example plus minus infinity. So, you have a final state, initial state u goes to t plus t minus I. This U matrix which evolves the initial states to final states just goes to F S I. This is the important thing, that the initial states are coming from large negative infinity in time essentially, and the final states are coming into the final states are going into the distant future essentially, or far infinity essentially. But these interactions can conserve some symmetries essentially. So, these interactions can conserve symmetries, say if they conserve baryon numbers, say for example, the number of baryons in an interaction can remain the same and so on. So, that will reflect on this particular S matrix essentially, the symmetries of the X matrix, and which will in turn depend upon the symmetries of the L interaction essentially. L interaction can have some symmetries. So, what we are trying to, the entire idea of quantum field theory is to understand this particular thing, that of the S matrix and this evolution. So, this evolution is the T matrix which we have written essentially, and so at a finite, for a small period of time they enter the interaction picture, and during that interaction picture they evolve like the interaction states which we have seen goes through the Dyson series, okay, which we see is going through the Dyson series. So, basically what we have to do is we take the initial and final states, okay, initial and final states as free particles, and S is nothing but your L interaction essentially, for all practical purposes essentially. So, the S is nothing but your interaction Hamiltonian. So, and so that is how the states evolve essentially. So, I and F states are eigenstates of H0, the free Hamiltonian. That is the main assumption we make it, okay. So, this is a big assumption essentially. So, this is a big assumption. So, this assumptions helps us to compute things essentially. And then there is this unitary matrix which takes this I and F, which are eigenstates of H0, takes one to another. So, it takes the I states into F states essentially through a matrix, unitary matrix. S is a unitary matrix which is also called the scattering matrix. Which is also called the scattering matrix essentially. So, there are so for all practical purposes essentially S is nothing but your L interaction, okay. S is nothing but your L interaction or H interaction. So, that is how you enter into your, or you want to be at the leading order essentially, which you put in your L interaction, but S evolves like the U state essentially. S is nothing but the U, the Dyson series which we have written at a small time interval, at an extremely small time interval essentially in the interaction picture. Okay. I hope you all get it essentially. So, at the leading order, so it S evolves like the Dyson series. So, at the leading order, in the coupling constant, this could be whatever coupling constant. Say for example, you can take y here or lambda, whatever coupling constant. So, here which is there should be a lambda. So, whatever the coupling constant at leading order in coupling constant, if you remember the Dyson series, it will be just the first term is nothing but HI interaction essentially. So, okay, at the leading order in the coupling constant, it is nothing but the L interaction. So, the leading order in the coupling, it is H interaction. Okay, so if we have so the same for the Yukawa couplings, or okay, let's take an example with say for example the Yukawa case essentially. So, for example, here you have d power 4x psi dagger of x psi of x phi of x. Okay, so now for example, let's take pi pi scattering in lambda phi 4, or this is the Yukawa coupling. So, the initial states could be okay nucleon, so it could be neutron proton. The final states also could be neutron proton, and accordingly you can work this out at the leading order essentially. So, the final states also could be neutron. You can actually calculate the neutron protons scattering cross section in this manner. Now, there is a couple of things. If you go at the leading order also, there is a couple of things which are important, which is we have to recover the propagator essentially. So, when you do this, what happens is you have to worry about time ordering, you have to worry about when you actually start doing the calculations. So, you can also try to do okay. So, if you put in the initial states here and then express everything in terms of, say, I do not know, B plus C dagger, and here we will say B dagger plus C, and this we say it as A plus A dagger, and put it back everything here, you will end up having some issues essentially. You have to worry about a state in which there is a Green's function. Okay, there is a Green's function which appears essentially because there is okay, if you put it back into this. So, what will happen is essentially you'll be picking up a delta function. Okay, let me just write it down for here essentially. Why not why be lazy a little bit. So, let's put f as I is equal to minus I g f d power 4 psi dagger of x psi of x integral. I am just introducing the meson state, okay, the meson state operators. So, this will be d cube k to e k, this is the relativistic normalization, a k a p dagger e power minus I k x 0. Okay. So this is okay. So what we are trying to do is create a meson state from vacuum, essentially what we are trying to do. Okay. So but okay, so what you are trying to do is create a 2 meson state in the vacuum, essentially from the vacuum we are trying to create a okay. So but what it introduces is a state with 1 0. So this is minus Ig f integral delta cube or 4 psi dagger of psi of x e power minus I p of x 0. Okay. Now what is this essentially? Okay. So this is a plane wave essentially. Okay. Okay. And then this picks up, this is a d cube k integral, this is a d cube k integral. It picked up a delta function, it picked up a delta function interaction essentially as a source for the meson fields essentially. So it creates a delta function source. This became because of this d power 4x and d cube of k. So you end up having e power I kx essentially ipx the delta function picks up essentially. So this delta function will be some sort of a source for the thing. So if you work it out you will see what will happen at the end of the day is f s I is equal to minus Ig 2 pi power 4 delta power 4 q1 plus q2 minus p. So you end up having just a delta function. Okay, if you just work it out essentially, okay, this is just telling you that the delta what do you mean by this thing is that it is just telling you that the momenta should be conserved. Okay, the 4 momenta should be conserved essentially. On the other hand, it is also telling you something that you will also end up having something called the propagators entering in the computation of this amplitude essentially. You will also have propagators entering into the computation of this amplitude. So the first thing is that at the leading order what we found is that there is this amplitude which is just conserving the energy momentum of this 4 momentum energy momentum 4 momentum conservation essentially. Okay. Okay, and this just tells you that for a I don't know meson decay to 2 nucleons or something, or a nucleon to decay, the momentum should be conserved. That is all it tells you. If you just take the plane wave amplitude, and this is just the plane wave amplitude. So each of the plane waves contributes to the momentum fraction essentially. That is all it tells you. But it also leads to propagators. Okay, we will see the propagators. Okay, we will do the propagators in the coming lectures essentially. So we will then see what happens if we have propagators, and we will have an exact calculation of our first amplitude. We will do it in 5/4 theory, and we will do also encounter something called the time order product should be equivalent to the normal order product of the fields essentially and their contractions, which we call it as the Wick theorem. So let me stop here essentially. So what we have seen is what is S matrix, how do you write it down. Just blindly putting each of the amplitudes into the S matrix into of this thing will obviously lead to the delta function conservation of energy momentum. Okay, but we will go beyond that essentially, and then we will see how once you calculate the propagators and everything how the cross section changes. Okay, I'll stop you it here and then I'll see you in the next lecture essentially. Thank you very much.